Thank you. All right, so this afternoon I'd like to describe the modeling component for the project, and specifically what we propose to do for developing a tool or a set of methods for identifying potential locations for vernal pools, and to do that in a way that is efficient and feasible for broad areas. Ultimately, whatever we develop would have to be appropriate and then ultimately adaptable also for the very significant study area in the North Atlantic region. All right, so why is this a necessity? So you saw from some of Steve's slides that it is indeed possible to identify vernal pools using manual interpretation methods, but if you've ever done that type of work, and it sounds like Matt in particular could probably attest to this, that it can be very laborious. And while it's effective, there are tools that hopefully and theoretically will help us make the process of remote identification more efficient. Unfortunately, there are also some processing methods, some newer processing methods that will also help us in this regard, but to this point, many of the remote sensing methods have tended to focus on really small areas. We need to develop a method that would be efficient for much broader areas. Fortunately, we were at a good point for attempting this type of work. LiDAR, one of the more important data sets that we're proposing to use, is becoming increasingly available throughout the United States, and especially the eastern United States and also in Canada. There are some improved processing methods that we can bring to bear. And in particular, we believe that object-based image analysis provides many exciting opportunities for this type of work, and I'll describe that in more detail in a moment. So our approach then will be to develop an automated method for identifying potential locations for pools using LiDAR, but also other data sets where possible and available. We will demonstrate the utility, hope to demonstrate the utility of this method using two test sites, one in the northern part of the range and one more towards the southern end in New Jersey. The northern one will be in Vermont. And we will focus on county-sized areas, so a fairly significant political boundary, but also has the side benefit of being the area at which many LiDAR data sets are collected. So I'll very quickly just describe some of the technology in case you are not familiar with it. So LiDAR, light detection and ranging, and the most important thing to remember about LiDAR is that it's an active sensor. So there is a sensor that emits a pulse of light to the ground. That pulse is reflected off of surfaces on the ground, and some of those reflectances are recorded by the sensor. And that's in contrast to more traditional forms of remote sensing in which they're passive sensors, and essentially energy from the sun reflected off of the Earth's surfaces is collected. So this is an active technology. Another important thing to keep in mind with LiDAR is that there can be multiple returns per LiDAR pulse. And this is really important for mapping features that are partially pervious. So for instance, if we have a building or the ground, we can have a LiDAR return. But with something like a tree, we can have partial penetration of that tree, and actually some of the LiDAR pulses will make it to the ground. And that information is vital for developing something like a digital elevation model or a terrain model. And this is information, of course, that you cannot obtain from regular or traditional forms of remote sensing. So for each LiDAR point then, we essentially have a three-dimensional fix, and we'll have that for features on the ground, but also within and under partially pervious features like trees. So this is what the initial product from LiDAR. It's a point cloud, and that point cloud has depth and texture, so it can be filtered to yield information about objects on the ground and the ground itself. So if we just take a look at a close-up, for instance, this is actually adjacent to Central Park in New York City. You can see that traffic circle very well in those sapling trees just from the point cloud itself. But there are many applications for LiDAR. One of the most fundamental is digital elevation model. In this case, we take the last returns from a LiDAR point cloud, and we can develop this terrain model. If we take the first returns, we can develop what's called a normalized digital surface model, and that's the height of features above ground. So if you queried any of these trees here in Central Park or one of those buildings, you would get the height of that feature above ground. All right, so that's a whirlwind explanation of LiDAR. I'll now provide a similarly whirlwind explanation for object-based image analysis. As the name suggests, the focus here is objects. And this is in contrast to traditional forms of remote sensing in which pixels are the unit of analysis. So objects are important in this case because by focusing on objects, we better approximate with high resolution data objects that are of interest to us, objects on the ground. And once we have an idea of actual objects that represent features on the ground, we can also perform contextual analyses. So this is how humans look at the landscape. We don't look merely at objects themselves, we look at the adjacent objects. So we look at contrast and tone and shadow. These are things that we can analyze when we're looking at objects rather than merely pixels. A couple other important things to keep in mind. Object-based image analysis also permits data fusion. So we can bring in LiDAR, but we can bring in lots of other data sets and analyze those things simultaneously. So it's a tremendous amount of information. And also finally, with the program that we use, eCognition, there's also the opportunity for enterprise processing, which basically means we can tile the data into manageable units and then process some of those tiles simultaneously. So it's a very efficient processing method. So eCognition, again, the program that we use for object-based image analysis is an expert system-based approach. We develop rule sets that will segment available information into objects, and then we try to classify them. So I'll give you an example here. So this is a normalized digital surface model. It shows features above ground. The first step with all object-based image analysis is to segment the image, which we can do. Once we've created objects, we can use a variety of methods to classify those objects. We can use the actual characteristics of LiDAR, we can bring in imagery, we can bring in thematic data, and what we ultimately hope to achieve, at least in this case, is a land cover map. And this is a land cover map in which trees have been mapped to the scale of, or I should say, tree canopy has been mapped to the scale of individual trees. And we can pick up features with LiDAR that are as small as these saplings that have been planted. We've performed probably 60 or 70 different assessments in the United States of urban tree canopy assessments using this technology. So we know that it's very useful and very effective. We've done some similar work with LiDAR in forest change detection. We've also used LiDAR for characterizing forests for habitat quality, so canopy gaps, and also looking at understory characteristics, which of course are important for some species. So we're confident that we can use this information also for vernal pools. So if we look at a known location for a vernal pool, you can see even this oblique view, there's a depression there. And if we look at the LiDAR point cloud, you can see very clearly there is a concavity on the landscape. So we know that the information is there then. It's a process of capturing that information and converting it into a form that is usable. So actually lots of work has been done with LiDAR in vernal pools already, or there's a growing database, or a growing body of literature. And many of these studies take a two-step approach to first identify depressions using a DEM, usually one derived from LiDAR, because it has to be a high-resolution DEM. And then secondarily, many of these studies have identified flow potential. Does a concavity, does a depression on the landscape have the capacity to fill with water, to be a pool? There have been some other methods used as well. Some studies have looked at LiDAR intensity, which is basically the intensity of the return, and that yields information. And also there's been some statistical modeling as well, basically regression equations that are looking for patterns among variables. All of these things are on the table as far as we're concerned, but at this early stage, we're quite confident that we would use at least these first two steps in some capacity. So I'll very quickly describe some of the data layers that we can bring in to eCognition for this type of object-based image analysis. So our first study site is Addison County in western part of Vermont. So in yellow here is the LiDAR tiles that are available right now for the county. This county extends from the shores of Lake Champlain, which is very agricultural, to the eastern part of the county, which actually encompasses part of Green Mountain National Forest, so contiguous forest cover. So one of the first layers we can bring in is a color infrared imagery, standard imagery many folks have. This is actually federal NAIP imagery, so it's imagery that's available basically for the entire country. In eCognition, we can bring in the raw point cloud for the LiDAR point cloud. Of course, you really can't see anything from this two-dimensional view, but there's a lot of information there on the ground, and eCognition can be used to directly examine that point cloud. We can also bring in a lot of LiDAR derivatives. So outside of eCognition, we created a digital elevation model, again, a terrain model, a high-resolution one. We can also create that normalized digital surface layer, which shows essentially the height of features above ground, and that can be very, very informative for canopy mapping. And I should point out, of course, that this area here that we're looking at is in the western part of Addison County, which is agricultural. We can also bring in another LiDAR derivative, which is essentially percent forest cover, also very useful for vegetation mapping. Another product that we can derive from LiDAR outside of eCognition is a flow accumulation model. So again, looking at the flow potential for parts of the landscape. And then in eCognition, we can also create some additional LiDAR derivatives. It's hard to see in this relatively flat area, but this slope map that we can develop from a digital elevation model. We can also create an aspect layer, if that is useful. And then we can also bring in thematic data sets. So this shows road center lines. Road center lines are available for probably every state in the country. That's useful thematic data. We can also bring in hydrology. Again, most states have that, pretty good versions. Once we have these thematic data sets in eCognition, we can create some additional derivatives. We can calculate the distance to water. So this is a distance grid that we've created. And these areas that are bright white are the furthest away from water. We can also bring in, if available, building locations. So Vermont has E911 points, which are useful. When we combine that information with road center lines, we can create a density map, which essentially identifies the areas that are most heavily developed in this particular area. And once we know that, we can use that for excluding areas that theoretically would be unlikely to support something like a vernal pool. All right, so we're at an early stage in our modeling, but I'll give you a hint of some of the things that we can do in eCognition. So as I just mentioned, we can use some of the information that shows where developed features are to exclude those features from analysis. And as you can imagine, with this particular study area that covers one of the most heavily developed areas in the country, in the world, basically the East Coast megalopolis, there are certainly areas that will not be of interest to us. Yet the complex matrix of natural features in urban and suburban environment we will want to be able to examine those areas because some of those pools that occur in urban and suburban landscapes might be quite valuable ecologically. So we can as the very first step, we can take that density grid that shows developed features, segment the image, and exclude those. Then we can also look at forest cover. So in this particular area of Vermont, it's unlikely that a vernal pool will exist in completely exposed areas without any type of canopy. This may be different for other parts of the country, but this is probably a reasonable assumption for this particular landscape. So we can map trees, essentially to the level, the scale of individual trees. We can smooth those areas out and identify forest patches. And we can then focus the modeling on only those areas. So this is another way of increasing the efficiency of this type of modeling exercise. So this part of Vermont, it has relatively few confirmed vernal pools. So I'll switch to a different part of Addison County. So this is in the Green Mountain National Forest, and there are 3 confirmed vernal pools in this area, so keep those in mind. So one of the first things we can do then is bring in that slope layer, and we can segment. Again, the very first step in any type of object-based image analysis, we divide the available imagery into objects, and we can then classify them. So in this case, I've just classified low slope areas. And you can consider these as seeds then. In eCognition, there are some wonderful tools that permit you to grow out from objects into adjacent objects. So we can do that with those seed areas essentially. We can grow in an iterative fashion into adjacent landscapes using essentially a slope criterion. That growing procedure will grow out until essentially higher slopes are reached. And in this fashion, we can then identify depressions on the landscape. So this took about a minute and a half to run in eCognition, and we identified these depressions on the right, or on the left I should say, is the entire scene. On the right is a close-up. We can smooth out some of the smaller features. And you see that from the slope map, we're indeed capturing areas with very little slope. So that's a depression. As you can see from the broader scale, however, we've identified a lot of depressions. So now the question is, can we refine this initial selection to a group of sites that have a higher probability of actually being a functional vernal pool? One of the easiest things we can do is bring in the thematic hydrology. In this area of Vermont, it's unlikely that the hydrology layer has captured vernal pools. So we can, from the very beginning here, eliminate these depressions that coincide with hydrology. So that eliminates some of those initially identified depressions. We can also start playing with some size criteria. We can identify very small pools. We also can identify some large ones, which again, in this context, perhaps not in every landscape, it's unlikely that we're going to find a vernal pool of that size. So we can eliminate a few there. We can bring in this flow accumulation layer and look at the potential for these depressions to capture sufficient water. And we can, in the blue here, are ones we've highlighted that have very low flow potential. So we can eliminate those. We can take that a step further, and we can grow into the adjacent areas from those initially identified depressions and further compare the flow accumulation. That eliminates a few more. We can look at the depth of that pool relative to the adjoining landscape features. So if there are really shallow depressions, it's again unlikely and probable that those will support an actual vernal pool in this landscape. And then we can do lots of contextual analyses. In this case, we can look at the spatial patterning of pools. In this case, we've identified a set of pools that are within 50 meters of each other. And perhaps those pools have higher habitat quality if there's a concentration of pools. We can then export that or finalize a classification. Here in yellow, we've identified pools that are clumped within 50 meters of at least one other pool. These other ones here are more isolated. So going back to our original view then of this scene, there were 3 confirmed pools. In our method here, our preliminary method, we've identified those pools, and we've also identified some other depressions that may or may not be functional vernal pools. So this is very much a process of identifying depressions, features on the landscape that could be vernal pools, and then incorporating as much additional information to refine that selection to a reasonable and realistic number. All right, so that gives you a hint of the preliminary mapping that we have done, and gives you a sense for the things that we can do. So where is LiDAR available? In the light green, you'll see the current distribution of LiDAR. These LiDAR data sets vary in age and quality, but as you can see, the Mid-Atlantic is very well represented. Parts of Virginia also has good LiDAR data sets. In New England, the gaps are starting to fill. I can't give you a timetable, an exact timetable for when we'll have complete coverage, but there's tremendous interest in LiDAR, and new data sets are being acquired every year. The same in Canada. There's tremendous interest in LiDAR. In some time frame, there'll be probably complete coverage for the entire study area. All right, so just to summarize some of our goals, then, we want to develop a rule set, or a set of rule sets that can be adapted for use throughout this significant region as LiDAR becomes available. The ultimate goal, of course, is to produce GIS-ready data that can be used by people in the field for field verification. There are a couple challenges that we should acknowledge, as you probably guessed from looking at this type of work. This is not something that a casual GIS user is going to be able to do. You do need software, and you do need some decent computers. You don't need a supercomputer to run this type of analysis, but you do need decent PCs that have enough RAM and preferably have multiple processing cores. But nonetheless, we're confident that there's enough interest and enough expertise at the state and federal level, at the university level, private conservation groups, that there will indeed be enough GIS shops that would be interested in continuing this work once the rule sets, the initial rule sets have been created. And then another challenge will be incorporating local knowledge. So if we develop rule sets, they'll probably be robust for identifying depressions in the landscape. But as you've seen in this example, there are lots of other factors that could affect what features actually serve as functional vernal pools. And ultimately, there'll have to be a transfer of knowledge from people on the ground in the different regions who know those things to the rule sets themselves. So that is one of the challenges of this approach. So coming from northern New England, this is the type of scene that I imagine when I look at when I consider a vernal pool. Obviously, there's tremendous geographic variability in vernal pools across this region. So at this point, we would offer a plea for help then. What are the things that we should be incorporating in our models? What are the things that reasonably will distinguish these depressions on the landscape from just depressions, from things that serve as actual vernal pools? So if anyone has any questions, I'd be happy to address them.